All right, here we're looking at factoring again, and today the big difference is we're going to be looking at some of the shortcuts and some of the quicker ways that you can do some of these factors. And the first one and probably the best shortcut that we have and the most useful is when we have trinomials that have an a value of 1. So if that a value is 1, here's what we can do. For example, and as we do more and more of these, you'll probably notice this. Before, we would do it this way. We would build a bridge and would come up with that -8, and the two numbers that multiply to -8 but add to the -2 are the -4 and the +2. And then what we would typically do is we would do our factoring by grouping. So I'd split up the middle term. I'm going to take that off to the side and show you the factoring by grouping. Where we'd rewrite the middle term using those values, and I'd group the first two together and group the second two together, and out of the first two I'd factor out the x. Out of the second two I'd factor out the 2. And so the two factors I would end up with here are the x minus 4 and the x plus 2. And the interesting thing that we find as we do more and more of these problems is the values that I had right here, the -4 and the +2, end up being the constant terms in each of these binomials. All right, so the trick here is we still build a bridge, but instead of actually going through the process of factoring by grouping, anytime we have an a value of 1, we can just go right to the two factors, say an x minus 4 and an x plus 2, based on the fact that it came up with a -4 and a +2 for the two values that multiply to the bridge but add to the middle coefficient. All right, and so when we see that action, that shortcut in action here, again, I'm going to start off. I'm going to build a bridge. That gives me a +12. Two numbers that multiply to the 12 but add to the 7 are going to be a 3 and a 4, a +3 and a +4. And now instead of splitting up the middle term and factoring by grouping, I can go right to the answers. My two binomials, one of them is going to be an x plus 3 because I had a +3 as one of my terms over here, and the other one's going to be an x plus 4 because I had a +4 over here as one of my values. And that's it. Okay, so anytime we have an a value of 1, we can do this shortcut. If we have an a value other than 1, then we have to split up the middle term and factor by grouping. All right? So same thing with the next one. Again, I build a bridge. That gives me a +15. The two numbers that multiply to +15 but add to -8 are a -6, or sorry, a -3 and a -5. Let's try that again. -3 and -5. And again, instead of splitting up the middle term and factoring by grouping, I go right to the two binomials. One of them is going to be an x minus 3 because of the -3. The other one's going to be an x minus 5 because of the -5. And that's it. All right? And same thing with this last one. Again, I'm going to build a bridge. So I build a bridge that gives me a -10. Two numbers that multiply to -10 but add to a +3 are going to be a +5 and a -2. And again, because I have an a value of 1, I go right to my two binomials, the x plus 5 because of the +5 and the x minus 2 because of the -2. All right? That shortcut can only be used, again, when the a value is 1. We can go right to the two binomials. All right? The next thing we look at is perfect square trinomials. And these are trinomials that always factor into the same binomial twice. In other words, a binomial squared. All right? And really, there's not much of a shortcut to be had here. But there's a little bit of one that we can use if we recognize a perfect square trinomial. So here's what we do. The easiest way to recognize a perfect square trinomial is to start off the same way we'd factor any trinomial, by building a bridge. So here I build a bridge. That gives me a 25. The two numbers that multiply to 25 but add to a -10 are a -5 and a -5. And that's how I tell that this thing's a perfect square trinomial. As soon as I get the same value twice here, the -5 and the -5, that means that I'm dealing with a perfect square trinomial, which means this thing's going to factor into a binomial squared. And really, without the shortcut, if I know it's going to be x minus 5 times x minus 5, that's x minus 5 squared. It's a binomial squared. Without that little shortcut of knowing that this is a perfect square trinomial, it's got to be something times itself, I would probably split this up into an x minus 5 and an x minus 5, because the a value is 1, and just split into two binomials, and then rewrite it as x minus 5 squared. Okay? But the idea here is as soon as we recognize that it's a perfect square trinomial, I can go into a binomial squared. All right. Same thing with the next one. I build a bridge. That gives me a 16. The two numbers that multiply to a 16 but add to an 8 are a 4 and a 4. So now I know that this thing is a perfect square trinomial, so I know it's going to factor into a binomial squared. So I just have to ask myself what times itself will give me this thing. Well, it's going to be an x and a +4, and I can use those two values that I had up top to figure that out. Okay. But again, without that shortcut, without recognizing this, I would probably just rewrite this as x plus 4 times x plus 4, which is then an x plus 4 squared. Okay, so it really doesn't save us a whole lot of work. The only place that it's really useful is in this last one. Here I build a bridge. that gives me a 9, two numbers that multiply to a 9 but add to a -6, or a -3 and a -3. And it helps to know that this is a perfect square trinomial right from the bat, because I know this is going to factor into binomial squared. Well, the first term would have to be a 3x, and the last term would have to be a 1, and I'm going to have to do a minus sign in between. And I figured that out this way. I just look at the first term and say, okay, what squares gives me the 9x squared? It's a 3x. Okay, what squared gives me the 1? It's a 1, and then this minus sign just kind of transfers. All right, and if we forget that there's a shortcut that exists here, what's going to happen is we're just going to end up splitting up this middle term using a -3x and a -3x, and we're going to factor by grouping, and we're still going to get the right answer. Okay, and so when we look at a shortcut, these shortcuts, really, we don't necessarily need any of them. I would hope that you adopt the shortcut of when we have an a value of 1. That one is really useful. For these three, this shortcut really doesn't save us a lot of time or work, so we're almost better off if we recognize that that's great, but if we don't, just split up the middle term and factor by grouping, factor the way we would normally factor the trinomial. Okay? One of our other big shortcuts deals with these things, and if I look at these and kind of treat them like trinomials for a second, when I look at an x squared minus 4, really that's like a trinomial that's x squared plus 0x minus 4. It's like we're missing that term in the middle. And if I were to factor this like a trinomial, I build a bridge, two numbers that multiply to a -4 but add to 0, or a +2 and a -2. Since I have an a value of 1 out here, I can go right to the two binomials. It's the x plus 2 and the x minus 2. Okay? That's how we would factor it as a trinomial, and again, we're still applying those same rules that we've always applied. I could split up the middle term and factor by grouping. That would work also. All right? Same thing with the next one. If I rewrite this, this is like an x squared plus 0x minus 9. And now I could build a bridge and factor. So I build a bridge, that's a -9. The two numbers are going to be a +3 and a -3. And again, because there's an a value of 1, I can go right to the two factors. It's going to be an x plus 3 and an x minus 3. All right. The last one, again, if I treat it like a trinomial, there's like a 0 in the middle. So this is like a 9x squared plus 0x minus 4. Again, if I build a bridge here, that gives me a -36, and the two numbers are a +6 and a -6. This one I can't use that shortcut that I learned on the first page. I have to split up the middle term and factor by grouping, okay, because of that 9 that's out front. So I do a 9x squared plus 6x minus 6x minus 4. And now I do my factoring by grouping. So again, the point here is that we could easily do these the same way that we've done each of these problems. Okay, I can still treat it like a trinomial and really just use that one method. So here I'm factoring that out. Here I factor out a -2. That leaves me with a 3x and a +2. And now my two factors are the 3x plus 2 and the 3x minus 2. And when we look at all these guys, when I look at the answers that I've gotten for each of these, I notice right away that each of these answers, they're conjugates. All right? Here it's an x plus 2 and an x minus 2. It's the same binomial with a different sign in between. Here it's the x plus 3 and the x minus 3. It's the same binomial with a different sign in between. Here it's a 3x plus 2 and a 3x minus 2. Same binomial with different sign in between. So these factor into conjugates, and this is what's going to lead us to our shortcut. And what we call these things, these are known as difference of squares. Okay? And if there's another shortcut that I think is really useful, it's this one. All right. The first one is when you have an a value of 1 going right to the two factors. That's a shortcut we should absolutely use. And the difference of squares is the other one. Okay. So difference of squares is when we're subtracting two perfect squares. And again, when you look back at these examples, look at the numbers that I'm using here. An x squared is a perfect square. 4 is a perfect square. X squared. 9. Those are perfect squares. 9, x squared, 4. These are all perfect square numbers. So when I have two things that are all perfect squares and I want to subtract, sorry, I shifted my screen a little bit. When I have things that are all perfect square and I'm subtracting, it means I have a difference of squares, and I can go right to factoring this thing into conjugates. All right? It means it's going to factor into one binomial and another binomial that are exactly the same, but one's a plus, one's a minus. Okay? For example, when I look at something like this guy, again, I have perfect square numbers here. X squared is a perfect square, 49 is a perfect square, and I'm subtracting, so I have a difference of squares. So when this factors, it factors into conjugates. One of them is going to be a plus, and one of them is going to be a minus. And then I just look at this and say, okay, what times itself will equal that x squared? Well, it's going to be an x. So those are my first terms. What times itself will equal a 49? In other words, the square root of that thing? Well, that's going to be a 7. All right, so my second terms here is 7, so it's an x plus 7 and an x minus 7. All right, so we kind of think of it in terms of the square root, and then we just do conjugates from there. All right, same thing here. This is going to factor into conjugates. One's a plus, one's a minus. The square root of the x squared is the x. The square root of 100 is a 10. All right, so again, I get the same thing written twice, but one's a plus, one's a minus. That's the shortcut here. All right, again, this is a difference of squares. This is going to factor into an x plus 9 and an x minus 9. One's a plus, one's a minus, and I'm basically taking the square root of each of those terms. Okay. Same thing with the next one. This one's a little bit trickier, and this is where this shortcut really saves us some time, is when I look at something like this. If I know this is going to factor into conjugates, one's a plus, one's a minus, well, what times itself will give me a 4x squared? In other words, what's the square root of all that? Well, the square root of 4 is a 2, the square root of x squared is an x. So each of these first terms has to be exactly the same. They're 2x. And then what times itself equals the 121? That's an 11. Okay, so it factors into a 2x plus 11 and a 2x minus 11. All right, and the reason we end up with binomials when we FOIL that out is because we know when we multiply conjugates, the middle terms cancel. And it's the same thing with the next one. If I look at the next one, here this is not a difference of squares the way it's written. I have to factor out a 2 first, which leaves me with an x squared minus 36. Remember, always look for the greatest common factor first. And now that I have that greatest common factor out, I can see that I have a difference of squares. That's an x plus 6 and an x minus 6. Okay? And again, if we had put a 0 in for that middle term and built a bridge, we could have factored this building a bridge, but then we'd have a greatest common factor left in one of our terms at the end. Okay? So try to factor out the greatest common factor first. That allows us to use a shortcut on this. All right, same thing with the next one. I factor out the 3 first. That opens us up to the possibility of a shortcut because now I have a difference of squares. So now I can factor this into an x plus 4 and an x minus 4. All right. So again, the 3 shortcuts we looked at here was when the a value is 1, we can go right to the 2 binomial factors. When you have a perfect square trinomial, you can immediately factor it into 1 binomial squared, so the same binomial times itself. And then when you have a difference of squares, these things factor into conjugates, same binomial with a different sign. Okay?